Okay, so today we're going to talk about integration, double integration, on non-rectangular regions. So the idea here is we want to do a double integral. We have some function of x comma y. We want to integrate it, a double integral, over some region. We'll call it D, f of x comma y. dA, like that. And we're going to see that this region is just going to be some sort of weird shape, right? We'll call that D. Now clearly we could always put D inside a rectangle. We're going to think of regions that are fairly simple, at least that they can be put inside boxes. We're not going to do anything crazy here. We want to know how to integrate these things. So here's our x and y, and we can think about it in some ways like this. So if we have, we can break it up into pieces just like before. So we can make a bunch of partitions in the x-axis, and then make a bunch of partitions in the y-axis, like that. And just like before, we take representative points inside these little boxes. We can tile out the whole thing. And we know that the integral is going to be, again, we take two sums, I equals 1 to n, and j equals 1 to m, let's say. And we take xi, yj, and add them up and times it by little dAs. We don't like those dAis because not all of the dAs will be the same. So we think of that as a, sorry, actually we're gonna make that a delta A. Not all the delta Ai's will be the same, ij. They might be different, especially if we have little corner pieces there. We might have to think of them as different. But in general, we can always do something like this. All right, so again, we have a double sum because what we're going to be doing is we'll hold j at some constant, and then we're going to be adding up everything in some row here, and then we'll do the same thing to the next row. We'll go move to the next j value, maybe j equals 2, and we'll add up everything from I to 1 to n over here and over there, and so on and so forth. And we do our hay farming just like before. And as you know, if you've ever seen a farmer's field, they're not all rectangles. Sometimes they're strange shapes, and farmers carry on even in strange shaped fields. They find a way to get all of their hay. Okay, so again, these sums are maybe a little bit more difficult to organize. We can write them down simple enough, but we do eventually have to come up with a constructive way to add them all up. And that, of course, is the challenge any farmer has, which is how do we till and plant our field? And at the end of the day, we have to bring our crop harvester over and actually draw a line, draw a path through our field to get all of our hay. Okay, so we go through like that, and then we add it all up. So in this case, what we're going to do then is we have to define what the boundary is. So for this particular one, we can think of it as actually being bounded by two functions. We can think of this bottom function here. I'm going to put a little dark squirrely line there, like that. We're going to call that line right there g of x, right? And that will be we'll call it our lower boundary, YL, lower boundary. And then again, we have a boundary on the top, and I'll squiggle that out too. And right there, that will be YU equals f of x. It'll be the upper boundary. Now, obviously, other regions might work out that it'd be better to think of functions of y that are equal to x, but it doesn't matter. The idea is that we can draw some sort of shape like this. For regions like this, for regions that can be bounded, so we actually say that y now, all the y values in D are going to be between f of x above and below g of x, right? So our region D, we actually want to define it as, we'll put a little squirrely bracket, it's the points x comma y, given that x is between, now we want to put x, there's an a there, maybe a b down there. So x is between a and b. Put a comma, and then y is again going to be between these two functions of x, g of x and f of x. Put a squirrely bracket. So again, D is the set of points x of y, and we put this vertical sign to mean given, or such that the following conditions hold. One condition is that x is between a and b, and y is between g and f, which are these two functions. Here's the f function, and then there is the g function. All right, so this, not every boundary can be created in this way, but certainly it covers a lot of really nice cases. So how do we write down our double integral then? So the abstract integral, when we write down the expression, we say that double integral of f over the region D, xy, dA. All right, so when we mean dA, we mean little tiny area elements. All right, and we have some function that lives on that space. And now we're going to actually write this down, and we're going to integrate over from a to b, and an integral from g of x to f of x comma y. And now we're going to put the y integral inside the dx. And what we can do is actually put our little square brackets there to indicate what we're going to do now is, as a hay farmer, we're not going to go through the rows of the field to collect our hay. We're going to go this way. I'm going to go vertically like this. Go up, and every time we go up, we put a pile of hay there. And so we're going to integrate along the y direction first. So here we're going to do y first. And after we've integrated through y, and we start at g of x down here, and we're going to end at the f of x function, the top there. And that's going to be different for every x value. So that's what we're going to do here. And then at the end of it, we're going to do, x last. After we're all done, we've got our piles of hay from all of the columns that we've integrated. And then we're going to go through and pick all them up. We'll get the net value will be the addition of all of those, and that becomes our integral totally. So this is the way of, so here again is the representation of what we'll call our, the abstract symbol for the integral, and here is a specific construction of our integral that allows us an actual procedure for computing it. So let's talk about an example. All right. So here's an example. Well, this is one out of your book, and so we're going to talk about a tetrahedra. So the tetrahedra is some sort of triangle-like shape. So it's going to have four sides. And they're all triangles. All right, so we're going to talk about a specific one. So we want to, the goal here be to find the volume. So our tetrahedra then is going to be the volume is going to be created by the plane defined by x plus 2y plus z is equal to 2, and that'll determine one of the sides, and then the lines x equals 2y, and also and then another line, z equals 0. All right, so that's a plane. I shouldn't say that's just one line. And then this is going to be a plane. So we've defined two planes and a line. All right. So in addition to that, we also have we want to bound it by another plane here, which is the x equals 0 plane. All right. So let's draw out what this is. So I'm going to draw my, oops. There's my z-axis right there. I'm going to draw x in this direction. I'm going to draw y, oops, y in that direction. All right, so we have this, so the z equals 0 plane. That means the xy plane is going to be a boundary for the thing. We also see this plane up here, this angle that's on an angle. So let's talk about what that is. So what happens when at z equals 0? Where are we going to be? So if I plug x plus 2y is equal to 2, right? So when z equals 0, what line is this going to create in the xy plane? So that's this equation here when z equals 0. And so I can write this out. So this is going to be y is equal to 2 minus x divided by 2. So it's going to be 1 minus 1/2 x. All right, so what's that going to look like in the plane here? All right, so when x is equal to 0, we're going to be at 1. Put 1 right there. And then when, so it's going to go down at a slope of 1/2. So it's going to have this, so at x equals 2, so 1, 2, it's going to go down there. So that's one of our lines, right? Another line is when x equals 0. So let's find another line for this plane. So when x equals 0, we're going to get 2y plus z is equal to 2. All right. So y, so sorry, so that means z is going to equal to 2 minus 2y. So when y is equal to 1, that's this point right here, we're going to be down there on the y-axis. Z will be 0. But then as y goes towards 0, when I put a 0 in here, I end up with just 2. So it's going to be 1, 2 up there. So we can draw a line going down like that. All right, so we're building out our tetrahedra. And again, it's going to be 4 sides. All of them are going to be triangles. All right, next we need to find out the line x equals 2y. All right, so where is that line? That's going to be in the it's going to be in the xy plane. So we need to find out where that is. So again, if y is equal to 0, x is also going to be equal to 0, so we're going to emanate out of there. So one of our corners of our tetrahedra is going to be the origin. And we're going to go forward like, and then we're eventually going to intersect this line out here. So we see that one way to write this then is actually y is equal to 1/2 x. I like it thinking of it that way so I can plot it in the xy plane the way I normally think of it. All right, and that's going to come out like that at a slope of 1/2. So I want to know where it intersects this other line. So here was the other line right here, and now I'm going to have it intersect 1/2 x. And where do they intersect? Well, that I'm going to subtract this over, so that becomes a sum, so that becomes 1 equals x. All right, so at the point x equals 1, so I'll say that's x equals 1 right there. They're going to intersect, so we're going to have a line that goes like that. So I'm going to write that point. That's going to be the point 1, 1/2. So is that the value of y? right? So y is equal to 1/2 x, and if x equals 1, we get 1/2 there. So that's the point there, and we should say also that z is equal to 0. We're still talking about this lower flat plane there. All right, and then finally we get a line coming down off of there, like that meets up. All right, so our tetrahedra is this thing right there. We want to find that volume inside this shape here. So what's going on here is we need to find a, so we see that there's clearly a base to this thing. And the base is this triangle that's down there, and I'm going to call that D. So what does D look like? Now if I put my, sorry, I'm going to move that over. So I'm going to put my base down here. Oops. So there's X, there's Y. We see that I'm just going to map this down. So there's a 1 there, and a 0, 0, 0 is down there, the origin. We see there's a 1 there, and the line is going to look like that going in. Oops. Oops. I'm trying to draw straight lines here. It's really hard to do sometimes on these little tablets. Okay, there we go. So that's my D. All right, so can we put this in form? All right, so D then is going to be the points x comma y such that x is, what is x between? X is going to be between 0 and 1, and y is going to be between 1/2 x, right? That was our function here. This is that function 1/2 x down here, and 1 minus 1/2 x over there. And so that's our function. So now, and what is going to be the function then? F of x comma y is going to be the height. It's going to be this top plane here. That's going to be my f. That's going to be the top of the f surface. But what is that going to be? Well, we remember this was that plane right here that came from this one right here. That's going to be that plane defined there. And we can write this out in a little different form. We've got to solve for z essentially. So z is equal to 2 minus x minus 2y. Okay, so that's my function. I'm going to call this f of x comma y. All right, so there's my y function. It's going to be 2 minus x minus 2y. All right, so now we have to actually, so if these are my two, so this is my region and that's my function. Now I want to set up the integral. So let's do this on another page. All right, so again, our regions were x comma y from 0 to 1, and from 1/2 x, y is contained between that and 1 minus 1/2 x. All right, that was our thing, and our function then is going to be 2 minus x minus 2y. All right. So that means I'll write my double integral out. So the volume of that tetrahedra is going to be integral over d f of x comma y dA. Okay, that's, again, this is the abstract definition of the integral. And this tells us the basic qualitative information. We have some function over some region that we've defined here, and some function we've defined here. And we're going to integrate over this area that's underneath, this area defined by d. And we want to find the volume, which is going to be the tiny piece of area times a height, which creates a volume. Okay, so let's write this down now in its operational form. We're going in the x direction from 0 to 1. That's right here. And we're going in the y direction. We're going from 1/2 x to 1 minus 1/2 x. All right, and so our function then is going to be 2 minus x minus 2y dy dx. Remember that dA is going to be written in terms of dy dx. All right, we could also write it in terms of dx dy. It doesn't really matter, but at the end of the day we want to actually do an iterated integral, so we want to actually do one dimension while we hold the other one fixed. And we've chosen to do the y direction first and then go to the x direction second. That's just how we've decided to do our hay farming. Remember, now we're doing our hay farming vertically, and we're going to, at the end of the day, go horizontal to pick up the hay piles. Okay, so let's talk about what we do now. All right, so we can write this down. So again, the outside integral is going to stay put, and we have to take the antiderivative with respect to, we're integrating with respect to dy, just with respect to y. So the x here in this case is going to be a fixed constant. All right, so that means 2 minus x is just a fixed constant with respect to the inner integral. And of course that constant, take the antiderivative of a constant, we get y to the power 1. Okay, minus, and then 2y. What's the antiderivative? What's the antiderivative of 2y? It's going to be just y to the second power. All right, and that will then, we have that there, and now we have to do limits of integration. All right, so the limits of integration are 1/2 x to 1 minus 1/2 x. All right, so now we have to go compute this. Again, we leave the outer integral alone, and now we're going to put this in. So we leave the 2x alone. Again, that's a constant with respect to the problem, and we're going to evaluate y at the difference of these two things. So that's going to be 1 minus 1/2 x minus 1/2 x. All right, and then here we do the same thing. Minus, we have 1 minus 1/2 x, quantity squared, because we have a squared part up there, and then minus 1/2 x, quantity squared. And we put a dx on the outside of everything. Now you see there's no more y's left in our problem. Now we have something that's totally in terms of x. That's the whole point of farming hay, is we do all of our rows, or we do all of our columns until we've done everything in column form, and there's no columns left to do. And now all we have to do then is just one single row to add them all up. All right, so we have to do a little bit of work here. So I'm going to do a little simplification. We have a 2 minus x. And this becomes a 1 minus x, right? And that becomes a 2 minus 3x plus x squared, right? And we're going to do a little bit more simplification here. And I see that minus sign comes down. I need to FOIL this out. We have a 1. And then we have a minus x. And then a plus 1/4 x squared. And likewise here we have a minus 1/4 x squared. All right, so those cancel, which keeps things a little simpler. And that becomes a minus. The minus, that becomes a minus 1, a plus x. So let's simplify this all out again. We have a 2, that stays the same. We have a minus 3x, so sorry, a 2 and a minus 1. There we go. So we have a 2 and a minus 1, that becomes a 1. Likewise, we have a 3x, and we have an x there, so that becomes a minus 2x in total. We have an x squared, and that's just by itself, x to the 2. All right, so now we've done all that reduction. This is what the true integrand is. So let's write that down here. 0 to 1, 1 minus 2x plus x squared dx. Finish this out here. So that's, what's the antiderivative of 1? That's x. What's the antiderivative of 2x? That's going to be minus x squared. Likewise, we have an x cubed, so that becomes a we have an x squared, so that becomes a x to the 3rd power over 3. All right, so now we're going to evaluate at 0 to 1. And because all of these are 0 at 0, all we have to do is add them up. So we have a 1, minus 1, and a plus 1/3. So the answer is 1/3. That's the volume of our tetrahedra that we defined. So thank you very much.